All right, let's jump right into this explainer. We're looking at a truly groundbreaking achievement from researchers at EPFL that just got published in Nature. And I mean, this is a monumental shift for modern optics. We're talking about shrinking a massive, powerful, tabletop-sized ultrafast laser entirely down to a microscopic chip. For decades, these ultrafast lasers have been, well, some of the most critical tools in science, but their physical footprint, that's always been a massive barrier. So today we're going to unpack exactly how scientists finally broke through it.
To really appreciate this breakthrough, you kind of have to wrap your head around the sheer scale of the problem scientists have been battling for 20 years. Imagine taking equipment that normally takes up an entire specialized optical table in a lab. We're talking hundreds of pounds, needing dedicated environmental controls, the whole shebang, and compressing all of that power into an area roughly the size of a match head. Honestly, it sounds like pure science fiction, right? But by completely rethinking how we manipulate light, the EPFL team, led by Professor Tobias J. Kippenberg, actually made it a reality.
Now, to understand the raw power we're dealing with here, we first need to define just how mind-bendingly fast a femtosecond pulse actually is. A femtosecond is 1/quadrillionth of a second. To put that into perspective for a minute, 1 femtosecond is to 1 second, what 1 second is to, about 31.7 million years. It's almost incomprehensible. And these ultra-short pulses are exactly what enable incredibly precise technologies, from, delicate eye surgeries to precision manufacturing and even optical frequency combs, which is the Nobel Prize-winning tech that powers the world's most accurate optical atomic clocks.
The contrast between that old, bulky reality and this new microscopic tech is just staggering. See, photonic chips manipulate light using microscopic structures called waveguides. They're etched right into a wafer, very much like how electronic chips direct electrical signals. Now, while photonic chips have done a great job miniaturizing a lot of optical tech for telecommunications, generating these high-energy, ultra-short pulses directly on the chip, that was a totally different beast. The traditional setups were simply way too large and way too expensive for anyone to really use outside of major, well-funded labs.
And because of those massive limitations, for over 2 decades, the idea of putting a high-pulse energy femtosecond laser onto a chip was basically seen as an impossible dream. It was widely regarded as the absolute holy grail of the integrated photonics industry. Researchers all over the world knew that if they could just figure this out, they could democratize access to the most powerful optical tools on Earth. But time and time again, the fundamental physics of trying to confine intense light into microscopic spaces, it just seemed to present an impenetrable wall.
But here's the thing. The EPFL team didn't just try to brute force a solution. As Professor Kippenberg points out, the answer wasn't adding more complexity. Actually, it was stepping back and utilizing a surprisingly elegant architecture that the entire integrated photonics community had basically overlooked during this decades-long race.
That overlooked, elegant architecture actually has a name. It's called the Mamyshev oscillator. This specific laser design had received, relatively little attention in the field of integrated photonics before this breakthrough. So instead of trying to force standard laser architectures to work at a microscopic scale, the researchers adapted the Mamyshev oscillator, simply because its unique properties perfectly aligned with the intense challenges of working on a photonic chip.
To understand how it operates, you can think of this design as acting like a color filter combined with a highly selective security bouncer for light. Here's how it works. The system places a nonlinear waveguide right between 2 optical filters. First, as an intense laser pulse travels through that waveguide, it expands into a broader range of colors. Then comes the filtering phase. Only the most intense, properly broadened light is allowed to pass through the filters and continue circulating. The weaker light, it just doesn't broaden enough, so the filters act like a bouncer, blocking it and removing it from the cycle completely.
Now, this elegant filtering process happens on a very specific material platform. Co-leading author Zeru Chu noted that this design is highly attractive precisely because this specific material, an erbium-doped silicon nitride chip, is exactly what makes that elegant filtering possible, and it does it without having to resort to exotic, impossible-to-build parts. By matching the right architecture with the right materials, they completely streamline the manufacturing process. It really proves that you don't always need overly complex components to achieve record-breaking results.
And beyond just simplifying the components, this choice solved a massive physics headache. See, normally, confining intense light into extremely small microscopic waveguides causes it to interact really strongly with itself. In most standard laser architectures, these nonlinear effects completely destabilize the laser pulses, basically ruining the laser's performance.
But the Mashivshiv oscillator elegantly bypasses this whole physics trap. It's just far less susceptible to those nonlinear disruptions, which makes it the absolute perfect match for the tight confines of integrated photonic devices.
Okay, so what's truly mind-bending here is the actual length of the laser cavity hiding inside this microscopic device. It is nearly half a meter long. Yeah, 42 centimeters of carefully controlled optical pathway required to generate and sustain these ultra-short pulses. If you laid it out in a straight line, it would literally be longer than a standard ruler.
But the absolute genius here is how they managed to mathematically and physically fold that 42-centimeter cavity down into an area roughly the size of a match head. Using those microscopic waveguides etched into the chip, they meticulously coiled and routed the path of the light. It is just a masterpiece of spatial engineering, making it dramatically smaller than conventional fiber-based ultrafast lasers, but without sacrificing a single millimeter of the required cavity length.
And the performance? Well, it speaks for itself. Despite the tiny size, it delivers a massive pulse energy of 1.05 nanojoules, along with an incredibly short pulse duration of 147 femtoseconds. Now, these metrics are monumental because they exactly match the performance of traditional bulky tabletop setups. The researchers didn't just shrink the laser, they fully preserved its immense power and precision, proving once and for all that chip-scale devices can actually compete in the big leagues of modern optics.
And here's where it gets really exciting from a production standpoint. Because these photonic chips can be manufactured at a wafer scale, just like standard computer chips, we could potentially produce over 1,000 of these powerful laser cavities simultaneously on a single wafer. Think about that. We are shifting from building these lasers one by hand on laboratory tables to stamping them out by the thousands in fabrication plants. This huge manufacturing advantage could absolutely crash the cost of ultra-fast lasers.
Dropping the size and cost of these lasers changes the game completely. Like co-author Zebru Q points out, achieving kilowatt-level peak powers from a chip you can barely even see means we can suddenly untether demanding applications from the laboratory. Technologies that previously required an entire dedicated facility can now be made portable, affordable, and most importantly, accessible.
So this technology is going to rapidly accelerate everything from how we track pollution to making the GPS in our phones wildly more accurate. We'll be able to deploy portable, affordable sensors out into the field to detect environmental pollutants in real time. We can integrate them into handheld tools for identifying hidden defects in manufacturing materials. We can push the absolute boundaries of advanced medical diagnostics right at the point of care. And, perhaps most excitingly, we can build compact optical atomic clocks that are going to revolutionize our future communications and navigation systems.
I want to leave you pondering this exciting frontier for a moment. Because if we can shrink tabletop femtosecond lasers onto a match head, solving a 20-year holy grail in the process, the future of optics is just entirely wide open. What other massive, expensive laboratory tools are out there, just waiting for an overlooked, elegant architecture to shrink them down and put them in our pockets? The toolkit of human discovery just got a whole lot smaller and infinitely more powerful.